All right, for the last lesson for the equilibrium chapters, we are talking about solubility, which means, of course, more ice tables. All right, what are we going to pick up here? So by the time you're done with this series of videos, you're going to be able to write a KSP expression for another compound. Yes, that's right, yet another subscript for K, but it is something that you already know. And you're going to determine the solubility of an ionic compound given its equilibrium constant KSP. You're going to determine the solubility of a compound in the presence of a common ion, including hydronium and hydroxide. All right, so what do we got? So sometime back in last semester, you learned about salts being either soluble or insoluble, and it turns out that, as in a couple other systems, it's not that it's completely soluble or insoluble, and they're equilibrium systems and can be treated as such. For example, silver sulfate was one of those salts that we told you was not really soluble. So you can actually think of it as an equilibrium between the solid and the ions, the dissociated ions in solution in this case, 2 silver plus 1 ions and then a sulfate ion. Now the equilibrium constants for these expressions you put together just like you do every other equilibrium constant expression. Concentrations of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients, and excluding pure solids and pure liquids. Now this is a very important thing to keep track of because these solubility equilibria have solids in them. So this is the, in case you're wondering, the subscript SP stands for solubility product, but again, it's just another equilibrium constant. And in the case of this, it happens to be equal to 1 times 10 to the negative fifth. So this tells you this is significantly smaller than 1, so this tells you that this is a highly reactant-favored equilibrium, which means not a whole lot of silver and sulfate actually dissociates and gets into solution. All right, so a question we could ask ourselves if we were so inclined is, what are those concentrations of silver and sulfate once equilibrium is established? And yep, that means more ice tables. To the ice table. All right, so here's our equilibrium system. And we will just get stuff going here. All right, so we've got our silver ions, our sulfate ions. So initially, we're just going to assume that we have none of these, which means we can assume some forward progress to make some. Now you want to pay attention to the stoichiometry here. If the change in the sulfate concentration is going to be x molar, then the change in the silver concentration is going to be twice that much, giving us 2x molar. And now the chemistry is pretty much done. It's algebra from here. So the KSP, as I said before, is equal to 1.4 times 10 to the negative fifth. That's equal to the silver concentration squared times the sulfate. So algebraically, that is 2x quantity squared times x, which is 4x cubed. Now this is a common mistake that I see, so please be sure to apply this square to both the x and the 2. I would see very commonly I would see this evaluated as 2x cubed, which is not correct. Or forget to actually, they'd square the 2 but not the x as well. So anyway, be mindful of that. So 4x cubed equals 1.4 times 10 to the negative fifth, which means you need to get familiar with your higher root function, so cube roots or fourth roots or fifth roots on your calculator. You should have one, and that is 1.5 times 10 to the negative 2. Now, what does that represent? this represents the equilibrium concentration of sulfate that we expect to see. So the sulfate concentration is going to increase from, if you were to take some silver sulfate and dissolve it in pure water, the silver sulfate would stop, would start at 0, would climb until it got to 0.15 molar, and that would be it. The silver equilibrium concentration, again, just because of the stoichiometry of that particular salt, is twice that much, or 0.03 molar. And so that's how you determine, given a KSP, the equilibrium concentrations of the ions, again in this case, if you're trying to dissolve them in pure water. So what would we say is the solubility of silver sulfate? This is a tricky question because everyone, or a lot of different folks in a lot of different fields, tends to have different definitions of solubility. And it's not so much a definition change as much as it is, sometimes it's just units. So chemists like molarity, so we could say that the solubility of sulfate would reflect, let's say, how many moles of silver sulfate that you could dissolve in 1 liter of water. This is another way of saying what's the highest possible concentration. So the idea is that and what would you link it to? Because we actually had 2 concentrations that we determined here, the sulfate concentration and the silver concentration. And now in this case, it's easier to use the sulfate concentration strictly because of the one-to-one nature of the dissociation. 1 mole of silver sulfate creates 1 mole of sulfate ions. So you can say that the solubility of silver sulfate is equal to that equilibrium concentration of sulfate, which is 0.015 moles per liter. So, and this is not a this is something that we'd actually call like a sparingly soluble salt. There are many salts that are far, far less soluble than that. All right, and that's how you deal with solubility. And this, by the way, is often called the molar solubility because its units are the same as molarity, namely moles of stuff per liter of solution. Now, just for the sake of completion, grams per liter is also a very, very common way of expressing solubility. And I just want to walk through figuring that out. Now, if you're figuring out the solubility from an ice table, you are likely going to get a moles per liter, the molar solubility, because the solubility terms in the equilibrium constants need to be molar concentration. But with the molar mass of our substance, which in the case of silver sulfate is 311.8 grams per mole, you can easily convert from one to the other. So the molar solubility, as we said before, is 0.015 moles per liter. And if we multiply that by the molar mass, you will see that the moles cancel. So that gives us a solubility of 4.7 grams per liter. And this often is, from a more practical standpoint, a bit more convenient, so that knows that for 1 liter of water you can dissolve 4.7 grams of the silver sulfate.